Welcome to Lecture 4.7, Jordan Canonical Form. Let's recall the spectral theorem from the previous lecture. If A is a linear map of an n-dimensional vector space, then X decomposes as a direct sum of the so-called generalized eigenspaces of each eigenvalue. So E lambda j is the union of the null space of all powers of A minus lambda j to the I. Now if X is finite dimensional, eventually this null space, these things grow as n gets bigger, but they will stabilize. Now, if we focus in on a particular generalized eigenspace, E lambda j, then that will be a direct sum of subspaces that are invariant under both A and A minus lambda j I. Recall that a linear map is invariant under A if and only if it's invariant under A minus lambda j I, because this scalar times the identity doesn't actually really change anything. That's something that we proved a couple lectures ago. As I've been doing, I will recall an old example where lambda has algebraic multiplicity 11, so that's the size of the generalized eigenspace. There's only one eigenvalue. And geometric multiplicity 4. That means there are 4 eigenvectors. So recall this example. So here, this is the null space of A minus lambda I, or the null space is spanned by those 4 vectors. These 7 vectors span the null space of A minus lambda I squared. These 9 span the null space of A minus lambda I cubed, and so forth. And so when I say that this is a direct sum of subspaces invariant under A and A minus lambda I, there I am specifically speaking about these rows. So that 5-dimensional subspace, the one spanned by these, is invariant under A and A minus lambda I, as is this. Oops, let me get my highlighter back. As is this, and this. Recall that if we have a vector space X that decomposes as a direct sum of subspaces Y and Z, and we take a basis Y1 up to YK and ZK plus 1 up to Zn, and we construct the matrix of a linear map A from X to X, then that basis, or then that matrix, is going to be in block diagonal form. So we're going to have 2 blocks, one of them corresponding to the basis for Y and the other one corresponding to the basis for Z. And the basis for X is just the union of these 2 bases. And when I say block diagonal form, it's going to be zeros outside of these blocks. So going back to this example, that means that we will have the matrix of A is going to be an 11. It's going to be an 11 by 11 matrix, and if we pick these guys as the basis elements, then in block form, what we're going to have is a 5 by 5 block corresponding to this invariant subspace, a 3 by 3 block corresponding to this one, a 2 by 2, 2 by 2, and then a 1 by 1. And that is going to be, we've already talked about how if you order a basis for these generalized eigenvectors, v1, v2 up to vk, then the matrix form for that is going to be a Jordan block. And the reason for that is because by construction, if we have vk and we apply a to it, then we get, let me say if we do a minus lambda I times vk, then we get vk minus 1. So a times vk, if we solve for a vk up there, this is equal to lambda times vk plus 1 times vk minus 1. So remember how we construct such a matrix. We take our basis v1 up to vk and we apply a to it. And then these things here are the columns of the matrix. So the first column, we're just going to have lambda times v1. The second column, a v2, is going to be lambda, or I should say it's v1 plus lambda times v2, and then so forth. And the last one's going to be vk minus 1 plus lambda vk. So notice how all of these columns are going to have, this is the top, this is the bottom, they're going to have a lambda on the diagonal entry and then a 1 immediately above that, except for the first one because there really is nothing above. So here's a Jordan block. So it's just a matrix, right? A submatrix that has lambdas on the diagonal, and it has 1s directly above that. By the spectral theorem, every matrix is similar to a Jordan matrix, a block diagonal matrix of Jordan blocks. Now recall that here I'm calling these, so all of these are blocks that refer to lambda 1, and then all of these down here are blocks that refer to lambda k. So think of this as like a block of blocks. And that's because, remember, by the spectral theorem, x decomposes as e lambda 1, the direct sum of these up to e lambda k, and the eigenspaces, there's going to be a Jordan block for each of those so-called rows of generalized eigenvectors. This is called the Jordan normal form or the Jordan canonical form of the matrix or of the linear map A. We proved in the previous lecture that two linear maps, A and B, are similar if and only if they have the same Jordan canonical form. When I say they have the same, what I really mean is there is some way to order the eigenvectors, the generalized eigenvectors, so they have the same Jordan canonical form. Because if you reorder things, you reshuffle those chains, then you're going to get the same matrix, but you're going to just permute the Jordan blocks. So now what I'm going to do is go back to some of our definitions about generalized eigenvectors and eigenvalues and characterize them. I'm going to summarize what we've learned. Characterize them both in terms of polynomials, in terms of eigenvectors geometrically, and also in terms of Jordan canonical form. Now, I did this a few lectures ago, but that was before we had proven the spectral theorem. So I said it was a preview. This is when we do this. This is what we will conclude. And even after we proved the spectral theorem, I then had to prove that you don't have these generalized eigenvector chains that merge. So you don't have anything like that, or you also don't have a eigenvector that's going to have multiple generalized eigenvectors into it. Well, I mean, I guess you can have multiple ones, but they're going to be equivalent in some quotient space. So look back to the spectral theorem that we did after that in the previous lecture for why we eliminated these cases. So I did say back in that original lecture that this is a preview as to what we will learn, and hopefully it made sense, but now we can actually formally state these characterizations. So let's get right to that. First of all, for each eigenvalue lambda, the algebraic multiplicity of lambda, often what you call the regular multiplicity in your introductory linear algebra course, it's just the degree of t minus lambda in the characteristic polynomial. Geometrically, it's the maximum number of linearly independent generalized lambda eigenvectors of A. So it's if you take all the vectors that appear in this little chain diagram in any chain corresponding to lambda, then that's the algebraic multiplicity. And it's also the number of diagonal entries of lambda in the Jordan canonical form, because each one of these things that has, so let's say this is v1, v2, v3, w1, w2, x1, x2, so forth. So each of these is going to correspond to a 3x3 Jordan block that's going to have lambdas on the diagonals. This is a 2x2. So clearly the number of diagonal entries is just the number of vectors, generalized eigenvectors, that appears in this diagram. Okay, that is algebraic multiplicity. Next up is geometric multiplicity. This is the dimension of A minus lambda I. which we can think of as the number of linearly independent genuine eigenvectors of A. And when I say independent, we say there's two eigenvectors, but there's really infinitely many because any combination is an eigenvector. But so what I mean is, what's the maximum number of linearly independent ones? In terms of our so-called chain diagram that you're probably sick of by now, it's the number of these chains, because this is V1, W1, X1. What are the genuine eigenvectors? They are these things. Each chain has one of them. It's the one that gets mapped to 0 via A minus lambda I. This is also the number of Jordan blocks corresponding to lambda, because for each of these chains, each of these chains corresponds to a Jordan block. And also notice why it's the dimension of A minus lambda I, because the null space of A minus lambda I, because what is that? Those are the vectors that get mapped to 0 right away. The index of lambda is the smallest d such that nd equals nd plus 1. Remember where nm is the null space of A minus lambda I to the m. In terms of our chain diagram, that's just the length of the largest chain. Because if you get to the tip of one of these chains, if you have this chain going here and you finally get to this VD, the fact that when it's equal to VD minus 1 means that if you go further, so VD is all spanned by these, VD plus 1, if you don't have any more vectors in there, then these null spaces will have not only the same dimension, they'll be the same. Now remember that that's also the degree of t minus lambda in the minimal polynomial, because if you have a VD here, which is d steps away from 0, you need at least A minus lambda I to the d iterations, or you need d iterations of A minus lambda I to send this all the way to 0. Fewer than this won't work, so the minimal polynomial has to have this in it, and more than it is not necessary, because this will do the trick. Similarly, this is the size of the largest Jordan block corresponding to lambda. Finally, A is diagonalizable if, well, by definition, it has a basis of genuine eigenvectors, or X has a basis. So remember, in terms of our chain diagram, that means that we have, so let's suppose it's 4 by 4. That means that the basis for the entire space consists of eigenvectors that get mapped to 0. So that is equivalent to say that there are no preimages. There's nothing here that gets mapped onto V1 or any of these eigenvectors. That means that the minimal polynomial has no repeated roots, because you only need one iteration of A minus lambda I for each eigenvalue. Now this is the picture for lambda, but you might have other eigenvalues. So you might have A minus mu I maps some z1 to 0 and so forth. But if for every eigenvalue each of these things has length 1, then we don't need any repeated roots. We don't need A minus lambda I squared or higher for any eigenvalue to kill off our basis of eigenvectors. Finally, that means that the Jordan canonical form is a diagonal matrix. In other words, A is similar to a diagonal matrix. So all of the Jordan blocks are going to be 1 by 1. And that's what the word diagonalizable comes from, is that it's similar to a diagonal matrix. And though I've shown this to you before, what I really want to emphasize this diagram that you first saw in a lecture on change of basis. So that says that if you have a linear map, A with respect to the old basis E1 up to En, then the change of basis matrix is V1 up to, you put the new basis in the columns, and that's the thing that maps from here to top to bottom. And so now this basis, this linear map up here, our basis is v1 up to vn. And so if you apply a to each of these, a up to v1 up to vn, that you get lambda v1, you get lambda 1 v1, lambda 2 v2, up to lambda n vn. So the matrix up here are the columns. It's literally a diagonal matrix. So D is equal to P A P inverse. So do P, then A, P inverse. Reading right to left, P A P inverse. So I strongly recommend understanding this picture of these so-called generalized eigenvectors in the chains, and also this change of basis picture, and how P is how the new basis up here, you go from the new basis to the old basis by a linear map or matrix P, where that new basis is in the columns. So understand these pictures; they will keep coming back, and it'll really serve you well to understand both of these things. For the rest of this lecture, we will assume that A and B are linear maps on X which commute. In other words, AB equals BA. I'm going to prove several results about this. Well, actually one result and then a specialization. But to do that, we need this lemma. If we take an eigenvalue, lambda of A, and let E lambda be the generalized eigenspace of A for that eigenvalue, so in other words, the union of the null spaces of all powers of A minus lambda I, then I claim that E lambda is also B invariant. We know it's A invariant, but I claim that it's B invariant as well. So in other words, X is as a direct sum of the A eigenspaces, E lambda, and then some other things. So what this says is that if we restrict B to E lambda, then it sends E lambda to itself. Now, I'm not a huge fan of this restriction. I think it's perfectly fine to just say, take B and sends E lambda to itself. And I think that the restriction is implied. I don't think we need this extra nonsense here. So I'm just going to use this notation. And let's think about why this is true. So E lambda literally is the set of all generalized eigenvectors of A corresponding to lambda. So if we take any, so here's the proof of it. Let's take any x in E lambda. Then by definition, for some integer m, some non-zero integer m, A minus lambda I to the m times x equals 0. That's what it means for x to be in this generalized eigenspace. It's a generalized eigenvector. Even if it's a linear combination of multiple basis elements from this generalized eigenspace, it's still a generalized eigenvector. So to show that B sends this space to itself, I mean, in other words, B of E lambda is contained in E lambda, we just need to show that B of x is still a generalized eigenvector of A. So then A minus lambda I to the m times Bx, we just have to show that that is equal to 0. And I claim that we can commute A, and I mean, I probably don't need to verify this, but let me just do up here. If AB equals BA, that means that A minus lambda I times B equals B times A minus lambda I. And similarly, if A minus lambda I to any power, or any nth power, A minus lambda I to the m times B is B times A minus lambda I to the m. So I can take this and I can swap the B and the A minus lambda. So I can write this as B times A minus lambda I to the mx. And of course, that is equal to 0. So this whole thing is equal to 0. And that's all we had to show. So what good is this? Well, I claim that it is the key technical lemma needed for the following theorem, which is if we have commuting linear maps A and B, as before, then there is a basis for X consisting of vectors that are generalized eigenvectors of both A and B. Now that's not necessarily saying they have the same Jordan canonical form. Let me talk about what this means and what it does not mean. So for example, if we take A to be the matrix 2, 2, 1, so I guess 2, 1, 0, 2, and we take B to be the matrix 3, 0, 0, 3, then A is not diagonalizable. It has an eigenvector 1, 0 that gets mapped to 0 by A minus 2i. And it's easy to check that the matrix, or that the vector 1, 1 gets mapped to that via A minus 2i. So here is a basis of generalized eigenvectors. We don't have really too much room to choose here. So any eigenvector has to be a scalar of this, and then that's going to determine what this thing is. So let's call this thing v1, and let me call this thing v2. Now B, if I were to ask you to find the eigenvectors for B, you would most likely just come back and say, oh, well, let's take 1, 0 and 0, 1. And you would be right. This is a linearly independent set of eigenvectors. That's a basis. But really, every vector of X is a basis because this is a diagonal map. So for any vector, BV equals 3B. It's a diagonal matrix. So what I can't do is just take this basis, just take any basis and say, well, this is these are eigenvectors of B, so they will be generalized eigenvectors of A. No. So we are forced over here to pick this for V1 and this for V2, but because A and B commute, these things are going to be generalized eigenvectors for B, and they will also be genuine eigenvectors. So these two vectors are the things that do the trick in this case. So notice that B is diagonalizable. It's diagonal, and A is not. So this is not saying anything. So the Jordan canonical forms have a very different block structure, and you can imagine how different this can get for larger matrices. Okay, so let's prove this. We will start by writing X as a direct sum of generalized eigenspaces of A. So let's write X as E lambda 1 sum E lambda 2 all the way up to E lambda k. And let's be clear that E lambda j is a generalized eigenspace of A, and I think it's fine to understand that these are all distinct eigenvalues. So now what we can do is apply lemma 4.12. So if we restrict B to any of these generalized eigenspaces, then because it is B invariant, we can decompose each of these into generalized eigenspaces of B. So here's kind of a picture. I don't know. Let's see. How do I want to do this? How about if I write over here? Let's write this guy as E lambda j. Let's write this as 1, the direct sum up to E lambda j, and then let me write this as, how about I j, where these are all generalized eigenspaces of B. So now, every single vector in this entire generalized eigenspace is by definition, a generalized eigenvector of A. And if we break it up further here, each one of these is also a generalized, consists entirely of generalized eigenvectors of B. So we can do this for all of this. So let me write this out. So this is E lambda 1, 1, direct sum up to E lambda 1. Let's write this as I1. And then the next one, we can write this as direct sum E lambda 2, 1 up to E lambda 2, I2. And then etc. until we get to this last one, which I will write as E lambda k 1 direct sum up to E lambda k ik. So now I have taken these little atoms and decomposed them further, and what I have down here, every single one of these individually contains generalized eigenvectors of B, but also generalized eigenvectors of A, because the original space that it came from is a generalized eigenspace of A. So what are we trying to show? That there is a basis for X consisting of generalized eigenvectors of A and B. And here it is. Let's take a basis for each of these guys here and take a union of that, and there we have it by construction. So, if we want to write this up, we can say let B, this is just, it's notationally, it's tricky, but it's not really not hard. So let B J 1 be a basis for E lambda J1, and then B J, how do I want to say, IJ be a basis for E lambda J IJ, and so forth. And then let's let BJ be the union of all of these things. So I don't even know if it's worth writing it up like this. So BJ1 union up to BJ IJ, and then by construction, B, which is B1 union B2 union B K is the basis we seek. And that's it. Now, let me say a bit about this. So with respect to this basis in this particular order, the matrix of A is going to be in Jordan canonical form. So by construction, JA is, we're going to have J, I don't want to do this again, J1, 1 all the way up to J lambda K, J lambda 1 up to, whatever that index is. I don't really care, because all of these correspond to lambda 1. So these correspond to lambda 1, these correspond to lambda 2, and all of these correspond to lambda K. However, as we've seen up here, the eigenvalues of B might be very different. Might not share any of the eigenvalues. Maybe B only has one eigenvalue. Maybe these are all the same. Or maybe B is diagonalizable. Or maybe the eigenvalues for B are dispersed. Maybe 3 has multiplicity 10, and 2 of them come in here, 3 of them come in here, and 4 of them come in here. Something like that. They're dispersed throughout here. And if that's the case, we don't get to redo the ordering of this basis. So in this case, the matrix of B with respect to this basis, I don't even know what I want to call it, M, let's just call it M sub B. It's not going to be a Jordan matrix because the eigenvalue, you might have lambda, and then lambda down here somewhere. We don't have any control over the order of this basis here. Now, if we reorder the basis elements so they correspond to these so-called chains of generalized eigenvectors, then absolutely we can write this matrix in a Jordan canonical form. So you can think of this as what you get by taking a Jordan canonical form of B and then permuting the rows and columns corresponding to some order. One corollary of this, which you will see actually probably a lot more frequently than the statement itself, because it's something you can do in an undergraduate algebra course, when you don't talk about generalized eigenvectors, is that if we have two commuting maps that are diagonalizable, then they are simultaneously diagonalizable. And by that I mean there is some invertible matrix P that diagonalizes both of them. And of course we know with our little picture that I keep coming back to that P is the basis. P consists of the eigenvectors v1 up to vn. So in other words, there is a basis of common, the basis for x of common eigenvectors for A and B. So A looks like this. This is A, this is P. This is some diagonal matrix. And then B is going to look, is also going to be from x to x. And with respect to that same matrix, it is going to be diagonal. But it might be a very different diagonal matrix because there's no guarantees that these have the same eigenvalues. So this is a special case of theorem 4.13, but this is a really common homework question or prelim or qualifying exam question. So it's something that I actually encourage you to, as an exercise, prove it directly. It's going to be very similar, but just instead of specializing from this, use this lemma and write. And you can write x as the direct sum of eigenspaces e lambda 1 up to e lambda k. And the proof really is pretty much the same. It's just you end in a little different place. Instead of saying there's a basis of common generalized eigenvectors, you can talk about the matrices. And you can say both of these are similar to a diagonal matrix. And I think I'm going to leave it there. See you next time.